So hello everyone, we are very happy to have Sanjaye Ramgoolam all the way from London speaking about Kronecker coefficients and lattices of bipartite ribbon graphs. And this is all motivated from physics when we'll learn more about this now. Thank you so much, go ahead.
Thank you very much, Greta, for the invitation. So yeah, this is this work on Kronecker coefficients and lattices of bipartite ribbon graphs. This is the paper. Indeed, there are quite a few motivations from physics, but I've tried to sort of abstract the sort of algebra combinatoric side and present the focus on that. So I'm going to do that and mention some of the motivations along the way. Feel free to stop me if there's anything pressing you want to ask. I'm happy to answer within the talk, or I'm happy to answer later on as well. Okay, so Kronecker coefficients are very interesting quantities. There are many quantities in symmetric group representation theory which are combinatorially constructible. For example, dimensions of E-reps of Sn. You have a Young diagram. What is the dimension? Or you just enter some numbers according to 1 to n if it's Sn, and you enter according to the rules defining standard tableau, and you count those. You can get the dimension of the corresponding E-rep. If you want characters, you have a Young diagram R. You have a conjugacy class rho, which corresponds to cycle structures. There's a formula where you count labelings of the Young diagram R with some rules that depend on rho. And once you count these labeled Young tableaus, these border strip tableaus determined by the Young diagram R and the conjugacy class rho, you sum them up with a sign. There's a function called the height. You define that. So basically, you count things, count labeled Young tableaus of some defined according to some rules, and you get the character. You have the positive ones, you have the negative ones, you count them, find the difference, that's the character. Similarly for Littlewood-Richardson coefficients. So, I mean, there's no analogous thing known for Kronecker coefficients. These are numbers of invariants in R1, tensor R2, tensor R3. These are 3 Young diagrams corresponding irreducible representations of Sn. Take the tensor product. You can ask how many one-dimensional representations appear under the decomposition of this when we decompose it under the diagonal action of where permutations act as sigma, tensor sigma, tensor sigma. So that number is the Kronecker coefficient, and either it's 0 or it is positive. So from representation theory side, we know this is the case. But unlike the case of these characters or Littlewood-Richardson coefficients, there's no concrete thing you can count which says, okay, this is the thing which is the Kronecker coefficient, at least not in general for general Young diagrams. I think there are some special results for special kinds of Young diagrams. So we know these numbers are non-negative, but there's no manifest positive construction analogous to the Monahan-Nakayama formula for characters or the Littlewood-Richardson rule. And indeed, there are formulae where you're summing large numbers of things. Again, these can be positive or negative. These characters themselves are constructible. There are things that you can get by counting something, but you have a large sum of things to do, and not clear why that sum is going to produce something non-negative. So question for a while has been, is there positive construction? For example, discussed in Stanley by Stanley in 99, by Pak and Panova, for example, recently. So this is what motivated this paper that we had, although we had been studying Kronecker coefficients for other reasons, but it seemed like we could make some contact with this question. So, oops, sorry, went to the very end.
Can I just ask a quick? So Monahan-Nakayama counts as a positive formula, even though there's a sign, or
So I mean, there are the positive counting, the positive diagrams, and there's negative diagrams or negative label diagrams. And so there are two positive things, and you take the difference. So I think that counts as a.
Well, that we do have actually for the Kronecker coefficient. So such a formula is known since at least 2008 for the Kronecker coefficient.
I see. So
Like
you can
standard,
count.
yeah, very standard applications of some combinatorial identities give you a difference of very large sets of objects that you count. So signed objects with a +1 and a -1.
But there we don't have an involution that would actually show that we can do cancellation and only positive things remain.
Yeah, we don't have any involution like that, of course.
So and the Murnagam-Nakayama rule, it's a combinatorial, but the characters themselves can be negative and positive, and it's really, and even the characters you cannot write as sign and then something that you know it's positive. So yeah.
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 So, okay. Yeah, to be honest, I would like to understand exactly the precise form of the question, but let me give you a construction where we're going to count something and it's going to give you the Kronecker coefficient, and then we can maybe discuss this again in what sense it approaches the constructibility question as has been posed in the form that it is of interest in computational complexity. So what we're going to do is we're going to approach the question of constructing. In fact, so what we're going to do for C square, the square of the Kronecker coefficient, we're going to just count it without taking a difference of anything. C square is going to be counted, and it's going to be counted as the number of vectors in a lattice obeying some condition. So, and the whole approach that we're going to take is to take a family of algebras K of n, one such algebra for every integer, and K of n is a subalgebra of C of Sn tensor C of Sn, where C of Sn is a vector space of dimension n factorial spanned by permutation sigma. So you take linear combinations of permutations and you can multiply them using the ordinary permutation product in the symmetric group. So this K of n has a nice combinatoric basis. So there are two things about it. One is related to pairs of permutations, and it has a nice combinatoric basis related to tensor invariants, so of UN. So let me just describe that. So think about the variable phi ijk, where I, j, and k range from 1 to capital N. They transform in the fundamental Vn tensor Vn of UN cross UN cross UN. And this is a conjugate variable transforms in the anti-fundamental. So people have been interested in what are called tensor models. They are some kind of generalization of random matrix theories where you're integrating over, in random matrix theories, you have random variables, random matrix variables, something like phi ij. Here you have 3 index objects, which are your random variables, and you are doing an integration over these. And so it is of interest to count the tensor invariants, the polynomial invariants that you can make out of phi's and phi bars. And because these transform as tensor products of V, these as V bars, the only way to get invariants is to take, for example, phi and phi bar, or 2 phi's and 2 phi bars. So you have to specify a degree, and then you count the invariants. So this problem has a nice representation theory formulation in terms of UN, but because of Schur-Weil duality, it's also related to S symmetric groups. And it has been considered in a couple of papers, one with Benjeloun, and it has also been considered, the same representation theory problem from a quantum information theory perspective has been considered in this paper. So we are thinking about invariants of UN. So you have the fundamental and the anti-fundamental, V tensor V bar. When you decompose that under the diagonal UN action, you have a representation of dimension, the adjoint of dimension n square minus 1, and the invariant. What does the invariant look like? Basically, EI tensor E bar I, when you have the standard basis, you can check that this is invariant. And that's something that can be written in terms of a Kronecker delta. You're summing over I and J, and there is a delta ij. So when you have little n copies, a bunch of copies of this V and a bunch of same number of copies of V bar, you can build linearly independent invariants. They'll span a vector space of dimension n factorial, and this follows from Schur-Weil duality. And explicitly, you can write what these invariants look like by taking these tensor product of these basic fundamental representation vectors and the anti-fundamental guys, bunch of indices J1 to Jn, I1 to In, and take these I indices, contract them using the contract them with the J's, but you could have I1 J1 up to In Jn, or I1 up to In with some permutation of these indices. And then you can do one of these sums, you got J1 to Jn, E bar J sigma of 1 up to sigma of n. So sigma is a permutation in symmetric group Sn. Well, this little n is the degree, is the number of E's that we are thinking about. Okay, that's that little n here. And capital N is going to be taken to be much bigger or bigger than n. So under these conditions, there are exactly n factorial independent invariants, and they look like this. And there's sort of a diagrammatic way to think about this. N equals 1 case, EI, E bar J, you're going to contract it. So you can just draw it as a line contracting here. N equals 2, there are two invariants. Sigma is identity or the swap. The identity you can draw like this, or the swap you can draw like that. Okay, so this is I1, I2, either contracted or you are contracting with a swap. So I1 here, I1 goes with I1, I2 with I2, I1 here with this one, and this is I2. So there's a relative swap here, and that is represented in the diagram. In general, you have the E's, the indices of the E's are drawn here, of the E bars here, and you have a permutation that describes the contraction. Okay, so now this tensor problem, we have degree n, so you have little n of these phi's, little n of these phi bars. Then these are just sort of, each of these phi ijk, you know, it's a variable. It commutes with these other phi's. So the problem of counting these invariants is the problem of counting invariants in the n-fold, there are little n of them, n-fold tensor power of this triple. But you have to symmetrize because these phi's are commuting objects, commuting variables. Likewise, these phi bars are commuting. So there is a way to count, to build these invariants. So we want things that are invariant in the UN. So there's one UN that acts here and here. There's another UN that acts here and here, and another UN that acts here and here. So you want UN cross UN cross UN invariants. So the way to do that, to make sure that it is invariant under this UN, you have to contract everything essentially. So these I's have to be contracted, the upper I's with the lower I's. And to have invariance for the second UN, you have to make sure these are contracted using another permutation, and these guys are contracted using a third permutation. Using this diagrammatic way of thinking, there is a sort of three colored lines corresponding to the three indices, and the phi's and phi bars are contracted according to the permutations. Sigma 1 for the first index. I haven't drawn the sigma 2 explicitly, but there's a sigma 2 and there's a sigma 3. So there are three, given any triple of permutations, there is an invariant that you can write, okay? And it's invariant for the same simple reason that these things are invariant, as can be checked directly. But we said,
so can I
yeah,
just
please.
ask to see if I'm following? Okay, so we're saying that we have this vector space up top, this tensor product of sim n's.
Yeah.
We have an action of un cross un cross un on that. We want to compute the invariance of the invariant subspace with respect to that action.
Yeah.
And you're saying that if I hand you 3 permutations, sigma 1, sigma 2, sigma 3, then you can hand me back a vector in that invariant subspace. Is that
Exactly?
okay? And have is the state, is part of the state, have you told me anything about like the vectors associated different triples of permutations, if they span, if they're linearly independent?
Okay, good. So that's exactly the next transparency.
Okay.
So the next transparency is that there are equivalences, not all of them. So these invariants, one triple is equivalent to another triple if the two triples are related by this kind of equation. So if I have another triple, you will get the same invariant if sigma 1 prime, sigma 2 prime, and sigma 3 prime are related to your first triple through a multiplication on the left by a gamma 1, again in Sn. It has to be the same gamma 1, and a multiplication on the right by a gamma 2, which is the same gamma 2. And those two correspond to basically the operation of sort of permuting these phi's here that produces a gamma 1, and the operation of permuting these guys produces a gamma 2. And there's a diagrammatic way of thinking about products of permutations. So that permutation gamma 1, that equivalence, which is related to sim n, these two equivalences translate into these equivalences under gamma 1 and gamma 2 multiplications. So the space of invariance is isomorphic to this. Well, there's exactly one invariant for every element of this double coset. So the elements of this double cosets are equivalence classes under this action. And so the number of invariants is equal to the number of points in this double coset, and they correspond to these 3 colored bipartite graphs. The phi's above can be viewed as one kind of vertex, the phi bars below as another kind of vertex. So they're black and white vertices, if you like, and the lines join the 2 kinds of vertices, but there are 3 kinds of lines where the blues join with the blues above join with the blues below, the black above with the black below, and so on. So
can I just make sure I parsed this correctly? Yeah. So you're saying that if I pick one representative of each of these cosets, then I get a basis for the space of invariance?
That's correct. That's correct. Yeah. And now it is known that double cosets of this kind have an algebra structure on them. And I will give some more concrete ways of thinking about this algebra shortly. But first, let's just count the dimension of that. So essentially, we're defining our equivalence classes by taking permutation triples and acting on them by permutation pairs. So whenever you have a group acting on a set, here the group acting is these gamma 1, gamma 2s. You can count the number of these things by the Burnside lemma. So you have one of the size of the group, which is gamma 1, the number of gamma 1 and gamma 2s, and you count the number of fixed points under this action. Now, what is the number of fixed points? Well, that's the number of triples, sigma 1, sigma 2, sigma 3, such that this product, gamma, sigma 1, gamma 2 is the same as sigma 1, gamma 1, sigma 2, gamma 2 is the same as sigma 2, and so on. And this is enforced by introducing these delta functions on the group, where delta a function of sigma is in Sn, is defined to be 1 if sigma is the identity and 0 otherwise. So you can write a formula for this, and these are permutations. You can simplify this thing, and the upshot of that is that the number of these invariants is a sum of the partitions P of n, and these partitions are weighted by what I'm calling sim P, where if P has pi parts of length I, sim P is this product, I to the pi factorial. So this can be simplified to that, and there's a concrete number for that number of invariants. Now, this is the delta function on the symmetric group. So delta function on the symmetric group is related to the character in the regular representation. And as a result, there's an expansion of the delta function in terms of characters, irreducible characters of the symmetric group. And the multiplicities are the dimensions of the irreps. So you can kind of take that previous formula and write it in terms of characters using this expansion. And then a bit of simplification of what you have leads to the statement that the number of invariants is also equal to the sum of squares of the Kronecker coefficients. These themselves are written in terms of characters using the formula that I showed you before. So basically, we have two formulae, this one and the other one in terms of Kronecker coefficients. So I will describe another graph theoretic way of thinking about the same counting, which is a ribbon graph theory way. And it's kind of related to a gauge fixing in physicist language of that permutation triple. We had a sigma 1, sigma 2, sigma 3. We're going to simplify that description so that we just have a pair rather than a triple. And the way we can do that is the following. You have this sigma 1, sigma 2, sigma 3. They are equivalent to these ones. Now, if you're given a sigma 1, sigma 2, sigma 3, you can pick your gamma 2. This is sort of gamma 2. You can pick the gamma 2 to be sigma 3 inverse. And then this can be written as sigma 1, sigma 3 inverse, sigma 2, sigma 3 inverse, which is this pair of permutations I'm going to call tau 1 and tau 2. On the other hand, you can take also your sigma 1, sigma 2, sigma 3. You can apply the gamma 1 equivalence to them, and then apply the gamma 2 equivalence, so that essentially you take the inverse of that, multiply on the right. So that this will become 1, and then this permutation, the inverse of that will appear on the right hand side here. So using this, you see that you have this tau 1, tau 2 on the one hand, and the conjugate of the tau 1, tau 2 on the other hand. So now we have reformulated it as an equivalence of pairs, where the equivalence relation is given by one permutation gamma, and the action of that one permutation is through simultaneous conjugation. Again, you can use Burnside formula like we did before, and set up this counting in terms of this delta function. You get exactly the same answer as before, which confirms that this gauge fixing argument is correct. So we end up counting pairs of permutations subject to this equivalence under conjugation by the same permutation on both sides. Now, this has a known combinatoric interpretation in terms of bipartite ribbon graphs, which are also called hypermaps. So these are graphs embedded on a two-dimensional surface. And from a graph theory point of view, they are sort of graphs with edges which have a local cyclic order around the vertices, which comes from sort of embedding the graph on a surface. This has been well studied for their books on these graphs on surfaces, for example. So just to concretely show this for the case of S3, we are looking at permutation pairs subject to simultaneous conjugation. And for example, if they're both identity, if you're doing S3, if you have three edges, they're both identity. That means we're looking at these graphs which have two kinds of vertices, black and white. The graphs are embedded on a surface, therefore all the vertices inherit one orientation, one cyclic orientation. So what you do is you label the edges, and then you go around the vertices and you read off. So here 1 is going to 1, 2 is going to 2, 3 is going to 3. So that's the identity permutation. Likewise, this one. Here you have this graph embedded on the surface. For the black vertices, as I go around each vertex, well, first of all, there are 3 vertices. So there are 3 cycles in the permutation. This is the permutation tau 1 and the permutation tau 2. There's only 1 cycle, so there's only 1 vertex. And as I go around, I read off the permutation 1, 2, 3. Here is sort of 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 3, 2. Some of these graphs can be embedded without intersection on the plane or on the genus 0 surface. So there's an associated genus. Here, if you respect the orientation specified here, you have to embed it on a genus 1 surface. So these graphs come with a genus and embedding on a surface. So essentially, the same counting of bipartite ribbon graphs, which in terms of permutations is simply this, is the same counting that we talked about before. So the counting of bipartite graphs is the same as the sum of squares of Kronecker coefficients. So this counting that we just talked about is now also the counting of bipartite graphs with n edges. So now associated, essentially we did something basically with Sn cross Sn. So rather than working with just this set Sn cross Sn, we can work with this vector space, C of Sn, tensor C of Sn. So in that vector space, well, which is also an algebra, in that algebra, we can think about the subspace, which is invariant under this simultaneous conjugation, which was the action which was defining these equivalences in the case of the bipartite graphs. So here we have sort of sort of equivalence classes, and here we're going to define an analogous thing, just a subspace which is invariant under these simultaneous conjugation. Now, and one can show that this subspace has the same dimension as the number of equivalence classes here. And the way to see that is that basically when you have these equivalence classes, tau 1, tau 2, organized in equivalence classes by the simultaneous conjugation, let's say R is a label for the different equivalence classes. As R goes from 1 to the number of ribbon graphs, for each equivalence class, I have some representative pair. If I take such a pair and I conjugate it with this, I just apply this averaging, this group action, which acts on both permutations by conjugation, I will produce something like this, which has the property that it is invariant under that simultaneous conjugation. Because if I put in these gammas, I can absorb them in these sums, and this will be invariant. So this is invariant. So it lives in this subspace, which we call K of n. And also, this can be simplified. Each orbit, so each such thing is one representative of an equivalence class. So the different elements within the equivalence class form one orbit under the group action. So the different elements within that orbit, which I'm denoting tau 1, tau 2 r sub a, you can sum everything in that orbit and take an average 1 over the size of the orbit. So you can show these two things are the same. So these live in the subspace, and you can multiply things like this and show that when you multiply them, you get something else which has the same invariance. So it's actually a subalgebra of C of Sn, tensor C of Sn. Not just a subspace, but a subalgebra. So these guys form a nice geometric basis, one for every ribbon graph. And this algebra has the property that its dimension is the sum of these symmetry factors, and it's also the sum of the squares. So basically, this is teaching us that the sum of squares of Kronecker coefficients has a nice combinatoric interpretation in terms it is equal to the number of ribbon graphs with n edges. So in this recent work, we asked ourselves, okay, can we, if we know that this sum of squares is equal to the number of ribbon graphs, what about a particular square of Kronecker coefficients? Is it the case that that C square can somehow be obtained from the space of ribbon graphs? And indeed, can we get C itself? Sorry, R1, R2, R3.
Can I just, this is kind of a minor question, but in that bijection between permutation pairs up to conjugacy and bipartite ribbon graphs, was there a labeling on the vertices of the graph, or somehow that labeling gets washed out in the...
Somehow the labeling essentially comes, once you know the permutation pair, that's enough. You don't need an extra labeling. You see, once you know, for example, these two permutations, there are only labels associated with the edges. And you know that each cycle corresponds to a vertex. So once you know that, because you have a labeling for the edges, you sort of have a label, implied labeling, but there's nothing beyond that.
Okay, but so there's a labeling of the edges of the graphs are, it's bipartite ribbon graphs with n edges, and the edges are labeled by 1 through n. So
if you think about labeled bipartite graphs, you'll get these guys. There's equivalence that we talked about is precisely the relabeling. So when I change the labels, I will just go to something else, which is something like that.
So can I ask just as an example? So in the top right, you have this 1, 2, comma identity permutation. If I compare that to like 2, 3, and then the identity permutation, are those?
Indeed, that's right. So that would be in the same equivalence class.
Okay. Okay, great.
Yes. So great. So essentially for each equivalence class, we have one of these elements in C of Sn, tensor C of Sn, and typical elements are sums or averages over these different representatives of the same thing, which is expressed in this equation here. So, and there's a closed associative product on these guys inherited from the group algebras. So the key idea to kind of refine this correspondence between these sums is to understand on K of n, we already have this geometric basis, the ribbon graph basis, but there's also kind of a Fourier basis, Fourier Transform basis, which is labeled by triples of Young diagrams. So there's going to be something else, which is a basis for K of n, labeled by triples of Young diagrams. There's Q, R1, R2, R3, and tau 1 and tau 2 are two indices that each go from 1 to the Kronecker coefficients. And these will be explicitly constructed. Well, there will be a formula for these guys. I'll show you later. But then we're going to look at what we call a Fourier subspace for a triple, which is the direct sum over these tau 1, tau 2s of this Fourier basis. And the dimension of that is C square. And well, there is a formula for this in terms of Clebsch-Gordon coefficients. But our construction is not to construct Clebsch-Gordon coefficients, rather is to use the known formula for this in terms of Clebsch's to recognize that this subspace that we've just defined can be characterized as the eigenspace of a set of operators. And there's a set of operators, tki, k goes from 1 to k tilde star, I goes from 1 to 3. I'll tell you what these things mean shortly. But there's a set of linear operators, and we can characterize this Fourier subspace in terms of these operators. And these operators we're going to actually look at those operators in the geometric basis in terms of linear. So we let them act on these ribbon graph basis vectors, and linear combinations of these ribbon graph basis vectors form this space, this Euclidean space. Inside here, you have integer subspace, which is the lattice of ribbon graphs. These TKIs that I will show you can be used to construct a linear operator, which is an integer. They'll be used to construct an integer matrix, and then the sort of the vectors in that subspace that I defined, the vectors in that subspace will be null vectors of that integer matrix. And then we will use kind of integer matrix algorithms to get these null vectors. So if you have null vectors of an integer matrix, if you're trying to solve this null vector equation for an integer matrix, there is a basis of solutions where the vectors themselves are integer vectors. So these will correspond to integer linear combinations of these ribbon graphs. So they will live in this in a sublattice of this lattice of ribbon graphs. And because this is the dimension, the number of them is going to be C squared. So that's the plan. And the next step is to kind of show you how to construct these integer matrices. And in order to get there, we're going to
may I ask a question?
Please,
So
yeah.
the plan was really interesting, actually.
Yeah.
Can you go one slide back, please?
Yeah.
About the integer matrix, and you want to. So you are searching for the null space of the integer matrix, and you say you want to construct a basis of that.
Yeah.
And so my question is: so this is a general theorem? I can hardly believe that you would have that you can find that there's a unique basis for any integer matrix.
That's wonderful. So that's exactly, there's some non-trivial facts about the group algebra of Sn that allows this to happen. And the next part is exactly to explain those facts.
Thanks a lot.
So indeed, so we're going to sort of look at look at the group algebra of Sn and the center of the group algebra, and think about Fourier transforms on that group algebra. And then we're going to apply the idea of Fourier transforms to K of n. And this will allow us to do this construction of C square. And then we're going to think about C itself, and that'll involve looking at an involution. If I have time, I'll talk about quantum mechanical interpretation of everything. So let's look at the group algebra of Sn. This we know. And then we want to look at the center of the group algebra. So linear combinations of things in Sn, which are invariant under conjugation or which commute with everything. So we want things which obey this for any gamma. How do we build these things which are commute with everything, so which are central? So there's one such central element for every conjugacy class. So you take some conjugacy class. So mu is a partition which specifies a cycle structure, a conjugacy class. And if you take all permutations in that conjugacy class, you sum them with equal weight, you get something in the group algebra which is central. You can easily check that. When you multiply these guys, two of these guys associated with two partitions, you are going to then get a linear combination of other things, other central elements like this, and these are integers. Just because they come from group multiplications. So now there's another basis labeled by Young diagrams. So you take a Young diagram R, take the character of permutation in that representation, multiply it with sigma, sum over sigma, that's the dimension of the representation, dr over n factorial. These are projectors, they obey these algebra, projector equations. And the connection between the conjugacy class basis and the projector basis is that if you take these central elements, multiply them by these projectors, then you're going to get back the projector with the normalized character, the character of the permutations in this guy. So it's the character of something there, if you like, character of something in that conjugacy class weighted by the size of that conjugacy class, or in other words, character of the sum of everything in that conjugacy class, divided by the dimension. Also, you can expand these central elements in terms of these central elements, and these are the coefficients. So these normalized characters are very interesting. So essentially, you have T mu acting on the center by left multiplication here. And for each T mu, there's a matrix n mu nu lambda. These you can ask, how do I diagonalize this matrix? So how do I diagonalize these multiplication operators? Well, the multiplication operators is the eigenstates of that multiplication operation are simply these projectors, because when you multiply these projectors, you get back this. So these guys are the eigenvalues of this integer matrix that you have here. So these normalized characters are eigenvalues. And we also know that these normalized characters are rational because of the Monahan-Nakayama construction. And combining these two facts, you know that these are in fact integers. So this is explained, for example, in Simon's textbook on representation theory. So they are very interesting normalized characters. So then there's this recent paper from a couple of years ago with Gareth Kemp, where we show the following, two related things. If you take the conjugacy classes of the form where you just have one non-trivial cycle, so partitions where one cycle of length k, where k is 2 or bigger, remaining cycles of length 1. So this is essentially cyclic permutations. So you sum the permutations in T2, just one swap, one permutation of type 1, 2, 3, but you sum over everything in that conjugacy class. So you get these central elements. So if you take T2, T3 up to Tn, these guys generate the center. Generate in the sense that if you start taking linear combinations of these, products of that, and so on, those linear combinations of products built out of this produces the whole center, which has dimension P of n. So you have only n of them, but you can generate the whole thing by taking arbitrary products of these things. A related fact is that these normalized characters, which are integers, for T2 up to Tn, here's a list of normalized characters. I can think about this for Young diagram R, and I can scan over Young diagrams. These lists of normalized characters, if I take T2 up to Tn, they distinguish Young diagrams. No two Young diagrams will have the same list of this kind if no two distinct Young diagrams. So basically, if you scan over the Young diagrams, these lists are going to be different. And this is related to this fact that T2 up to Tn generate the center. The fact that these generate the center uses some results about the structure of that multiplication algebra, T mu, T nu, that I mentioned, which are proved in the book by McDonald. And the connection between these two facts is a fact about, essentially, it's a fact about linear combinations of projectors and how these can be used to generate the whole algebra of projectors. In fact, you can generate the whole algebra if you take a linear combination where the coefficients are all distinct. So that's a fact also recently used in this representation theory paper by these guys. So using these two facts, these are the two important lemmas, that T2 up to Tn generate the center, the normalized characters distinguish Young diagrams. Now, in fact, you don't always need the whole T2 up to Tn, just kind of interesting fact that if you just take, for example, the normalized character of T2, this distinguish Young diagrams, and you can check this in GAP, for n equals 2, 3, 4, 5, 7. If you take T2 and T, it doesn't work for 6. If you take T2 and T3, you can generate you can distinguish Young diagrams for everything up to n equals 14. And if you take T2 up to T6, you can distinguish everything up to 79. So basically, there's a number k star. For any n, there's a k star, usually much less than n, such that if you take all these t's up to k star, you can build a list that distinguishes Young diagrams. So for what we do next, we're going to pick a k tilde star, which can be anything from k star up to n. So to make it more efficient, you would like it to be as close to k star as you like, but we don't exactly know this function analytically or whatever. So, but you know, so that's a higher order question. You can pick, for example, just n, so that's fine. So, the next thing is sorry about that. The next thing is that there is a Fourier basis in the center of the group algebra, where you take the matrix elements in an orthogonal representation and you weight them with sigma, and that forms a basis for the group algebra. So actually, I don't really need this fact because I don't have that much time, so I'm going to skip this. But maybe just one thing, if you take these sort of cycle operators that I just talked about, and you multiply these Fourier basis guys, you get exactly these normalized characters. And there's a generalization of this statement to k of n, which we will use next. So good. So now we want Fourier transform on k of n. So great. So we have this algebra. This is the dimension. This is the geometric basis, which we have talked about already. But there's also a Fourier basis. The Fourier basis is if you like, a sum of permutations in Sn cross Sn, but we are in the group algebra, so I'm allowed to take linear combinations. So you take the matrix element in some orthogonal representation, in orthogonal representation R1 and R2, you pick some orthogonal basis, and you multiply by these matrix elements, but then you also multiply by Clebsch-Gordon coefficients, which are essentially, you know, these essentially tell you how the invariant, which is labeled by tau1, appears in R1 tensor R2 tensor R3. So there's some number of invariants, or another way to think about it is VR1 tensor VR2. Take two Young diagrams, tensor the representations, decompose them into E-reps. There is a change of basis from the product basis, if you have some orthogonal basis here, into this new E-rep basis. And that change of basis is the other Clebsch-Gordon coefficients. And you know, you can always choose a basis where this form an orthogonal basis for this tensor product. And you have this orthogonal basis, and the overlap defines the Clebsch-Gordon coefficients. So this formula is a little bit complicated, but essentially you can use these Clebsch-Gordon coefficients to build the Fourier basis for that algebra k of n. And its Fourier basis, it has these properties. This complicated object is indeed invariant under simultaneous conjugation by gamma. Tau1 and tau2, they go from 1 to c, so there's c square of them. And they multiply like matrices. So R1, R2, this product is going to be the same exactly when this triple is the same as this triple. And these indices will multiply like elementary matrices. So basically, this gives you an explicit Wedderburn-Artin decomposition of this associative algebra. So whenever we have an associative algebra, which is a nice non-degenerate pairing, there is a decomposition of that algebra into matrix blocks. So this is what this is doing, explicitly using Clebsch-Gordon coefficients. So we're not going to construct the collapses explicitly, but we're going to use that formula to show that the Qs essentially that I just showed you obey these conditions. They can be characterized as eigen states, eigenvectors of these operators built from these central elements in Sn. So I built some central elements in Sn from taking the sum of the permutations in a cyclic conjugacy class. So you can do that in one factor, you can do that in other factor, you can do that with the permutations acting simultaneously in both factors. These define three kinds of operators, tk1, tk2, tk3. So essentially, these guys identify, these guys have these characters, which are these normalized characters. But we also said that if you take enough of these k's from 2 up to k star or k tilde star, you can completely fix the Young diagram. And we're going to use that fact to say that the linear operator, that we can take these operators, t2 up to tk tilde star, their eigenvalues will distinguish the triples of Young diagrams. And therefore, we can look at those operators on this geometric basis now. And geometric basis is just, sums of permutation pairs. This is also sums of permutations. So this product can be re-expanded in terms of this geometric basis, some coefficients, again, coming from permutation products. So these are the number of times, this is the number of times the elements in that permutation sum, when you multiply it with a fixed element in the orbit R, produces an element in orbit S. So this is an integer matrix. So these tki get represented by integer matrices on the geometric basis.
Can I just try to, so this space V, R1, R2, R3, can you remind me what that is? Is that the matrix block associated to R1, R2, R3?
Exactly. That's exactly what it is. So you have the, the direct, so it's a linear, arbitrary linear combinations of these matrix block elements, yeah.
And do we know at this point that the dimension of that is the square of the Kronecker coefficient, or that's something we'll learn later?
No, that we know from generalities, because by the construction of these Qs, these come from these taus here. They label the multiplicities that R3, the multiplicities for R3 appearing in this tensor product. And that's another way to think about what the Kronecker coefficient is. So the dimensions of how many times R3 appears. So I have permutation representations R1, R2, act diagonally, decompose into E-reps. The multiplicities are the Kroneckers. And for each, and therefore there are these overlap coefficients which have this multiplicity index. So we are using precisely those multiplicity labels. So by construction, there's C squared of them. So we know there's C squared of them, but we haven't actually constructed them because we haven't built the collapse coordinates. What we will do instead is to recognize that elements in that block subspace are eigen states of these tk operators. And then we're going to look at these tk operators in the geometric basis. So then we're just looking for the eigenstates of that matrix. In other words, we're looking for the null vectors of the matrix minus its eigenvalue. And we need T21, T22 up to tk tilde star 1. For each of them, I have a corresponding eigenvalue. And these eigenvalues, they are integers. They are constructible from the Monahan-Nakayama construction. And these are integers constructible from multiplication of these tks with the ribbon graph permutations. And so we have an integer matrix whose null vectors are precisely the vectors that live in that V. And there are integer matrix algorithms for constructing the null vectors of an integer matrix. I have a few transparencies there, but I think for time I won't spend too much time on this. But essentially, there are gap. This exists in gap. You can do this using H&F algorithms. It's described in textbooks on computational number theory. For example, if you have this matrix, integer matrix, you're trying to find its null vectors. Here's a null vector. These are linear combination of the columns that are 0. Whenever you have such null vectors, you can reduce that matrix to Hermit normal form, and that reduction involves writing a Hermit normal form matrix. So it's a triangular matrix of a special form related to the matrix you're interested in. Whenever that M has null vectors, then its Hermit normal forms has a bunch of rows with zeros in them, and the corresponding row in the U gives you the null vector. So this is a fact about how to get null vectors using integral algorithms with integer matrices. So basically, you have that very explicit integer matrix. You can construct C-square using that. And that's a way to get C-square vectors that live in this lattice of ribbon graphs. And there's an involution which acts from K of n to K of n. It acts basically, you have, K of n is sums of permutation pairs. S acts by inverting both permutations. And once you have inverted the permutations, you can ask, for example, given a ribbon graph represented by a pair, or given any permutation pair, if you invert both of them, you can ask, is there a gamma such that simultaneous conjugation of that original guy gives you the inverses? If that is the case, we call it a self-conjugate ribbon graph. If that is not, we call it non-self-conjugate. Basically, this action of inversion descends to a nice action on K of n itself. And you can ask, how does it act on the Q basis, for which we have a formula? Essentially, the action of this involution just swaps the tau1, tau2 labels. That means that to get vectors which obey S equals 1, you just have to take the diagonal guys, Q tau tau guys, or sort of tau1, tau2 plus Q tau2, tau1, with tau1 not equal to tau2. So adding those up, there's CC plus 1 over 2. And if you want to get S equals minus 1 in the Fourier basis, you just need to take the Q tau1, tau2 minus Q tau2, tau1 with tau1 not equal to tau2. So that just gives you the number of them. There's this one, but again, we don't explicitly construct the Qs. Rather, we work with this X matrix which identifies the Young diagram, and then S equals 1 is another linear condition, which is sort of an integer, can be expressed in terms of integer matrices, and that's the big integer matrix. Null vectors of that gives you C plus 1 vectors. If you instead look for S equals minus 1, you get CC minus 1 over 2 vectors. And so you have two sets of vectors. If you choose some injection from the smaller set of sublattice from the set of vectors here into the set of vectors with S equals plus 1, any null vector algorithm will produce a list. So you can just pick an injection, and whatever is left the number of that will be C. So I'll skip the quantum mechanics stuff. Essentially, the upshot of the quantum mechanics stuff is that instead of working with rectangular matrices, you can work with square matrices. And instead of working with the TKIs and stacking them together, you can take some integer linear combinations of them, which still distinguish these Young diagram triples. So due to time, I won't spell that out. Maybe just some remarks and open questions. Would be nice to know this K star of n. How does it behave as a function of n, especially as n becomes large? This will help estimate the complexity of this algorithm for calculating C square and for C. it would be nice to understand a bit more in a canonical or geometrical way how to choose a map from this CC-1 up to this and this bigger set. So we don't really understand this very. I mean, you can choose one, but it would be nice to choose it in a nicer way. Another question is that we have sort of made the connection between Kronecker coefficients and the sublattices using representation theory, using the fact that the TKs act on the Qs to give you these normalized characters. But of course, we just have that integer matrix. An interesting question is, if you just took that integer matrix, can you show purely combinatorially from that integer matrix whether you're going to get C squared? I think that's related to a question I was being asked before. So we don't know. We have to use some representation theory input to know that you're getting C squared. So if we could find a way to work directly with integer matrices and prove these things, that would be an important step forward as well. You can do similar things with Littlewood-Richardson rather than Kronecker's. Instead of tensor invariants, that corresponds to two matrix model invariants, and the corresponding Qs and so on have been constructed. In fact, this kind of construction of Qs is motivated by applications in multi-matrix models. And this kind of work has been done in the context of physics and ADS-CFT. So I will stop here.
Thank you very much.
Can I answer the